Discrete Mathematics Project. What is a QR code? Do you know how does a QR code works, how the data is stored in it, how the encoding algorithm works, how error correction works? If don't, then let me show you. A project guided by Prof. Manish K. Gupta, Prof. Manoj Raut, Prof. Prosenjit Kundu. Mathematics behind QR code. DA-IICT, Gandhinagar. Contents. Introduction. Data representation and finite fields. Reed-Solomon codes. Data placement and QR code creation. Introduction. A quick response QR code is a type of barcode that can be read easily by a digital device and which stores information as a series of pixels in a square-shaped grid. QR codes are frequently used to track information about products in a supply chain and often used in marketing and advertising campaigns. QR codes are considered an advancement from older, unidimensional barcodes, and were approved as an international standard in 2000 by the International Organization for Standardization, ISO. Data representation and finite fields. QR codes encode text represented as binary numbers. The QR code standard allows for text strings to be created using 4 encoding modes: numeric, alphanumeric, byte, and kanji. The byte mode of encoding text for QR codes utilizes the ASCII character set. Each character in ASCII corresponds to a decimal number, which can then be expressed as a string of 8 binary digits, or a byte. ASCII table. Here we first have converted the text into ASCII value and further it will be converted into the binary code, with the help of finite fields. Each and every character has an ASCII value assigned to it. We have shown some of it in the table. Different QR code versions have different character capacity. The character capacity of some different version is shown in the table. For more information you can refer to the PDF file attached in the description box below. For example, for this website URL, the following can be expressed with the help of finite field in binary form. Expression is given below. You can see that the data is converted into binary form and then represented in 8 bits or 1 byte. Reed-Solomon codes have been used extensively to correct data transmission errors in mobile phones, compact discs, satellites, space probes, and numerous other examples. The objects in which Reed-Solomon codes can actually correct errors are finite field elements, in a field containing 2 to the power m elements for some positive integer m, generated by a primitive polynomial p, x, of degree m, with primitive element a. To create a Reed-Solomon code, the desired maximum number of position, that is polynomial coefficient, errors guaranteed to be correctable upon the arrival of information at its destination must first be chosen and specified. Let t be this desired maximum number of position errors guaranteed to be correctable, which can be any positive integer t with 2t less than n, where n is equal to 2m-1 is the number of non-zero elements in the field. Reed-Solomon codewords are polynomials consisting of a prefix and a suffix. The prefix of a codeword is constructed starting with a polynomial of the form, where prefix polynomial is m, x, and generating polynomial is g, x. The suffix polynomial s, x, is the remainder when the prefix polynomial is divided by g, x. That is, if x to the power u multiply by m, x, is equal to q, x, multiply g, x, plus s, x. With degree of s, x, less than the degree of g, x, or s, x, equal to 0, then the suffix is s, x. Codeword formulation. In this table you can see different version of QR code have distinct number of codewords. For more information you can refer to the PDF file attached in the description box below. Placement of codewords in QR code. The coefficients of each prefix are written consecutively in order across the rows of a matrix, and then taken in order down the columns of this matrix, skipping over any blank entries that may have resulted from prefixes of different lengths. The coefficients of each suffix are written consecutively in order across the rows of a matrix, and then taken in order down the columns of this matrix. The interleaved prefixes and suffixes are then joined together to represent the data. Data placement and QR code creation. Inside QR code, we have 6 types of patterns. They are message and error correction data, format information, finder patterns, alignment pattern, timing patterns, quiet zone. A QR code formats a message with specifications and places the result on a two-dimensional grid made up of pixels. QR codes can have grid sizes ranging from the smallest for version 1 at size 21 by 21 to the largest, as of this writing, for version 40 at size 177 by 177. Each new QR code version after the first uses a grid size with 4 more rows and 4 more columns than the grid size used in the previous version. The size of the grid for a particular message depends on the number of characters in the message and the error correction level specified for the code. A QR code of version 4 is essentially a 33 by 33 matrix. In figure, the message and error correction data is located in the small dark blue and light brown squares. Each square in this data placement represents a binary digit, for which normally a 1 is represented by a darker color, dark blue, in this case, and a 0 by a lighter color, light brown, in this case. The regions outlined in red in figure are reserved for the format information, which is a string of bits giving, among other things, the error correction level, L, M, Q, or H, for the code. The format information also gives the mask pattern, which we will describe in more detail later. Error correction bits are also included as part of the format information in case any of the information is lost. The function patterns consist of the finder patterns, alignment patterns, and timing patterns, as well as a dark module, which is a single black square located directly above the format information block near the lower left corner of the matrix. Finally, a quiet zone is included, as indicated in yellow in figure, as an area of lighter color designed to enclose the main QR code matrix. QR code data placement. Starting in the lower right corner of a QR code matrix, the data for each codeword prefix, suffix is placed in blocks in an up and down pattern. Each primitive power element is color-coded to illustrate the codeword prefix, suffix with which it is associated, as well as how the interleaving spreads each codeword prefix, suffix throughout the matrix. For each individual block, the 8 binary digits representing the primitive power element are placed in a zigzag pattern. The region bit placement summary section in figure A indicates the order in which the binary digits are placed within similarly shaped blocks, with the coefficients of each polynomial of degree 7 representing each primitive element power placed in descending degree order. QR code masking. After the data is placed into the QR code matrix, to make the data as readable as possible by a QR code scanner, the process of masking is applied. When data in a QR code is masked, particular data squares, depending on their location in the matrix, are flipped, with a dark square becoming light, and vice versa. After masking, a QR code is ready to be output. Conclusion. We showed the basics of how data is formatted and placed into QR codes, with error correction included via Reed-Solomon codes. Maplets written by the authors were used to demonstrate this. These maplets are available for download. The QR code generated in this paper focused on specific data that was generated for a particular version. Additional explanations for how other data can be formatted and placed into QR codes of other versions can be found. Associate members: Divya Patel, Kritarth Kadia, Harshit Prajapati, Shravan Kakadia, Ramkumar Patel, Kavit Patel. Thank you.